Hello, everyone. Welcome to Chapter 8, Chemical Composition. It's been a little while, kind of a long road, but we're going to start doing what a lot of people would consider chemistry now. We're going to talk about how we decide what is in our stuff, what's in our compounds and our substances, um, and how to begin to analyze this and connect it to chemical formulas. Very important concept in chemistry. So let's start by talking about counting by weighing. We have to do this with very small things, right? Think about fruit, one of my favorite things, nails. If you have to buy a bunch of nails to make a fence or whatever, and you're going to buy like a bucket of nails, how many nails is that? What other things do we have to buy in bulk? Fruit, nails, all kinds of produce and so on. Jelly beans. What, at some point, you're probably going to have to do something like make cupcakes or some other thing for your kids when they're in school, like your parents did for you. And if you want to put like 2 jelly beans on every Halloween cupcake for your kids' class, how many bags of jelly beans do you need to buy? This is the kind of thing you need to do. And we actually do this all the time in our lives. And we just want to think about how we do this for on an atomic level. So in order to do this, we're going to need to know or assume an average mass. And of course, if we think about one of my favorite fruit, cherries, cherries come in all different shapes and sizes and colors depending on the ripeness or the type of cherry. And of course, every cherry is not the same, but what we're going to do is we're going to assume an average mass. So we might weigh some sample of cherries, say 20 to 30 cherries, right? This is a small enough number that we could count them out and put them on our scale. And use the average as the representative mass. So if we used 31 cherries and say this was 306 grams, right? Then we can say one cherry is 306 divided by 31, or pretty close to 10 grams of cherry, right? This is 306, 31. This is, again, I probably should have had this done. This is 9.9 grams per cherry. So we could take this as the representative mass of a single cherry, right? So this is a very important kind of technique we have to do, just figure out the average. And then let's say that we wanted to put one cherry on top of 256 cupcakes. I'm not sure you'd really want to put a cherry on top of a cupcake, but that's what I'm going with here, right? How many grams of cherries would we need, right? And you want to give yourself, of course, a little wiggle room, right? Because you don't want to sell yourself too short and figure out this number exactly. You want to give yourself maybe, let's say maybe 10% extra, but we'll not consider that here, right? So we say, okay, 9.9 grams for one cherry. And we multiply this by 256. Let's do full dimensional analysis, right? Cupcakes. And we're going to multiply this now by one cherry on one cupcake. So that's the full dimensional analysis. And we're going to have to end up with, all right, so when we multiply this out and do the math, we're going to get 2.53 times 10 to the 3 grams of cherries, right? And this is 2.53 kilograms, of course, because 1 kilogram equals 1,000 grams. This should be a conversion that you're well acquainted with by now. And of course, we could figure out how many pounds this is by applying another conversion, and this would be 5.6 pounds, right? If we had to go into one of our grocery stores here in the States and actually figure this out. And so maybe you'd want to get 6 just to make sure you get enough cherries. Anyway, this is an example of how we count by weighing very commonly using food. Right, here's the example in the book. They're using jelly beans. Maybe you like jelly beans more than cherries. First, we have to find an average, and then we can multiply to find the mass of a thousand beans. All right, so now let's think about atoms. Atoms are unimaginably small, right? It's taking cherries to an extreme. They're so small, we really don't even have an idea of how small they are, how much they weigh in grams. And actually, I will say that usually when I start talking about this with students, I don't want you to try to think about the size of or the mass of an atom in grams. We're going to leave this to the end because it's such an unimaginably small number, and there's actually a really easy way to know what it is in terms of things that we know. But I'm going to leave this to last. So atoms are really super small. It's hard to understand their size. So first, let's think about the concept of relative mass, right? So relative mass is kind of nice because if we can use different kinds of atoms to figure out the mass of them to each other, a relative mass, we don't really need to know the absolute mass, okay? So in other words, if I say that this atom, if I define this as 1, okay, so what I'm going to do is I'm going to say that I want to use this one atom as my reference, and I'm going to define its mass as 1 unit. Now I have another atom, this blue atom, and I want to figure out the mass of this compared to my black atom. So all I really need to do in some way is put these on a scale, right, that makes them equal. And what I might find, for example, is once I put the blue atom here, that this requires 5 black atoms to balance it. So I can say that this blue atom is 5 units of mass. And I would say that this is relative to the black atom, right? This is the idea of relative mass, right? Let me catch up here. Now, it turns out that the way we do this in a modern sense is using something called a mass spectrometer, right? So a mass spectrometer is an instrument that first, well, what basically happens is it throws atoms, right? And it uses some physical properties to separate them according to mass. So a real simple example of this is, what if you had a bag of softballs and a bag of heavy shot puts, heavy shot, I'm sorry, not shot puts, heavy shot or small cannonballs, right? And what you want to do is you want to measure how far you can, and let's not try to throw them, right? Because let's not try to break our arms, but let's put them, right? Have you ever learned how to shot put something? So let's put them, right? And you're going to put a softball and you're also going to put a shot, right? So you don't break your arm. Well, it should be pretty clear that you would be able to put the softball farther than the actual heavy shot, which is like a cannonball, right? So in other words, the distance you can fling them is in some way proportional to their mass. And you could figure this out through the physics, the physical properties of these things. Well, the problem with atoms is they're really small. We don't have little people that can throw them the same way that we can throw massive objects. So we have to apply some tricks. And these tricks depend on the magnetic and the magnetic and the charge properties of these species. So it turns out if these things are charged, then we can use electric and magnetic fields to move them. So if we look here, the first thing that happens is we take our sample and we ionize them, right? We ionize these atoms. And then what we're going to use is we're going to use an electric and a magnetic field to kind of fling them. And the first is an electric field to kind of throw them. And then we use a magnetic field to bend them, right? It bends them. And the amount that they bend is going to be proportional to their mass. So what we find is we find that we can separate them according to relative mass. And if we define one of these masses, the lightest one probably, as 1, we define this as 1, then what we are able to do is figure out the relative mass of each of the other atoms in our sample. And this is a mass spectrometer. So we can find the masses of these things to a very high degree of sensitivity. So what we can see is the mass spectrometer is able to fling atoms, and this flinging allows us to figure out their relative mass. And their distance is determined by their relative mass, right? So the question is, what are we going to define as the base unit? What is one mass unit? Well, first of all, let's call this 1U. This is an atomic mass unit. Now, your book uses the term AMU, but this turns out to not be technically correct. The International Union of Pure and Applied Chemistry doesn't like this term. They like the term U for unit, one atomic mass unit. And so that's what we're going to go with. Now, it makes sense that we kind of know, right, that the atom with the smallest mass is hydrogen 1. Hydrogen 1 has 1 proton and 1 electron. And we also know from an earlier discussion that the mass of the proton is about the same as the mass of a neutron, which is much more than the mass of an electron. So most of the mass of atoms comes from the proton and the neutrons in the nucleus, right? So it makes sense that we would use the mass of a hydrogen atom as 1 unit, all right? So it turns out this is not true, and I'll talk about this shortly, but let's say for now, 1U is about the mass of 1 hydrogen, right? Now, um, it turns out that it can be very difficult to use this for a number of reasons, right? One of the reasons is that naturally occurring hydrogen consists of a bunch of different isotopes, right? And we'll talk about isotopes in the next chapter a little bit more. But let's say for now that the average atomic mass of an element is the weighted average of all masses of the isotopes of an element, right? Isotopes give different masses, and we'll say that the average atomic mass is the average over all naturally occurring isotopes. Okay. So if we look at the periodic table, if we look at a section of the periodic table, the numbers in the periodic table, these masses, not the mass number. Now remember, the mass number is an integer. The Z is the atomic number. And these things I have circled here on the periodic table, these are the average atomic masses of the elements, right? And we know these to pretty high degree of certainty. In other words, many decimal places. For example, carbon is 12.0107 U. So carbon 12.0107 U is the average or apparent mass of a single carbon atom in U. This is very similar to the cherries. Now, it may be just like the cherries that we could weigh 5,000 cherries and never find a cherry that weighed exactly 9.9 grams, right? That's just an average. Just like when we report a test average after everybody takes a test, it wouldn't be surprising if nobody got exactly the average score, especially if it was like 75.3%, and the smallest amount of points you could get on a test might be 1. So nobody could get 73.3% on a test, but they wouldn't seem unusual to you, right? Because you understand the concept of averages. And so it goes with atomic masses too, the average atomic mass. Okay. All right. So in carbon's case, it turns out that carbon atoms are carbon 12, carbon 13, and carbon 14, right? So these are the masses. And what we can say without being very super specific about it is that the mass of carbon 12 is about 12 U per atom. The mass of carbon 13 is about 13 U per atom. And the mass of carbon 14 is about 14 U per atom. So the average of these three numbers is 12.010. I have to go look, see that last number, 7. So one thing you should be able to see from these numbers, and it's an average, right, is that naturally occurring carbon is mostly carbon 12, right? Because the average is very close to the mass of carbon 12 atoms, which is going to be very close to 12 U, right? It turns out that the percent is about 99% carbon 12, about 1% carbon 13, and almost no carbon 14 naturally. And I see I made a little bit of a mistake here. I said 14, 14, and that of course should be carbon 14. Okay. Okay. Well, so we have this average mass of carbon, and since atoms are so small, anytime we pick up a little teeny tiny hunk of carbon from nature, it's going to have this natural abundance or natural breakdown. So we need to use the average mass of carbon anytime we want to use carbon or any other element, right? And we use, again, we use the periodic table masses to represent the average masses of the atoms. Okay, so how do we use this for an example? Well, we just use this average 12.01 U. Let's keep this to 2 decimal places. This is pretty common in chemistry to keep things to 2 decimal places. And we just use it as a conversion factor. So what's the mass of 431 carbon atoms? Well, we write down 431 carbon atoms, multiply by this conversion factor, 12.01 U is 1 carbon atom, right? And we put that into the conversion. We cancel out the carbon atoms and we get the answer 5176U. Now, in this case, this is actually going to be 5180U, right? With the proper number of sig figs. We should pay attention to that. But remember, the conversion factor is considered exact. So that doesn't limit us. The 431 does, right? Let's do another example. What's the mass of 75 atoms of aluminum? Well, we just set up 75 atoms of aluminum, use the conversion factor. We get this from the periodic table. If you look at the periodic table, the mass, the average mass of aluminum is 26.98 U. Multiply this out, and we get 2024 U. And again, this is probably more sig figs than a report. Maybe we would just say 2000. Actually, there's a little bit of a question I want you to think about. If I have exactly 75 atoms, that's a counting number, right? That's an integer. And the conversion factor then becomes the limit, right? So if we use the mass 26.98, you could argue that the conversion factor limits us to 4 sig figs, but not just 2. So this is actually a pretty good answer.
All right, so let's return to the concept of a mole, right? This is just a number that we're going to use as a scale up, right? So we realize atoms are so small that anytime we weigh out macroscopic quantities, 10 grams, 5 grams, even a microgram of atoms, we are always going to have huge amounts, right? Billions upon billions upon billions of atoms. We will always have some unimaginably huge amount to work with. And I keep saying unimaginably because I really don't want you to worry too much about what this number, the number we're going to talk about is such a huge number, we just can't wrap our heads around it, right? And in a sense, it doesn't really matter what this number is. And there's nothing magical about this number. It's just a number that we come about through definition, right? So we have all these atomic masses that we've compiled in the periodic table using things like mass spectrometers and so on. And we have to talk about two things. We have to talk about the actual definition of one atomic mass unit, right? And I started off by saying that one atomic mass unit is roughly the mass of hydrogen, and that's true. That's true. And but it turns out defining hydrogen as 1 U is not convenient. First of all, hydrogen exists as H2 gas, right? So it would be nice to use something as a reference that was actually the natural form of that substance. And hydrogen atom is not the natural form of hydrogen. Hydrogen exists as hydrogen molecule, right? Well, then you could say, well, why don't we just take half the mass of a hydrogen molecule? And we could do that, right? That would essentially be the same definition, but we'd have to have hydrogen 1 molecule, right? In other words, we wouldn't be able to end up with using deuterium, hydrogen 2, or tritium, hydrogen 3 in any part of our hydrogen molecules, right? So we have to do some separation or sampling, right? And this starts to get messy when we consider isotopes. The other problem is hydrogen and gas, right? It's really hard to put a gas on a scale. It tends to fly off the scale. It's hard to weigh. So gases are difficult to weigh. Let's spell this properly. gases are difficult to weigh. So let's avoid using gas. Let's use a solid or a liquid. Eliminating a gas from consideration eliminates many common elements like oxygen or nitrogen or the halogens fluorine, chlorine, right? And let's look at something that's a solid, easy to find or create, right, as a reference. And this brings us to carbon. Carbon is an abundant element. It's very easy to acquire some carbon. All you have to do is burn some paper, burn something that gives you a bunch of black carbon at the end, right? And we're going to use carbon 12, right? There's also this kind of idea that, remember that the massive parts of an atom are the protons and the neutrons, and they have very similar masses. They almost weigh the same, but not quite. They're a little bit different. So maybe it would be good to average over these masses, and further, maybe average over the mass of the electron that's in there, right? So if we look at carbon 12 has 6 protons, 6 neutrons, and 6 electrons. It seems very symmetric, right? So maybe this is a good candidate for that kind of symmetry of averaging over all the subatomic particles. And this is exactly what we do. So what we're going to do is we're going to define 1U is defined as 1/12 the mass of a carbon 12 atom. This seems kind of silly at first, but it's a very regular and easy to define definition, right? So this is going to be the definition of a U. It turns out over the years that many different definitions have been used, but we've settled on this, and I don't think we're going to move away from this definition. So it turns out everything, the relative masses of all the elements are defined through carbon, right? So now we have a good solid definition of what a U is, and we have all these masses in the periodic table of all the elements in U. So now let's go back to the scale up and the definition of a mole, right? We've spent so much time and trouble, scientists have anyway, defining these atomic masses in the periodic table. It seems like it would be silly to have a set of different numbers just because we have a macroscopic amount of stuff, right? And this is where the definition of a mole comes from, right? So what we want to use is we're going to say the mole. We have a symbol for this, right? Na. We also have another name for this, Avogadro's number, is the number of carbon 12 atoms in exactly 12 grams of carbon 12. Again, this seems kind of redundant, but it's not. You have to be very careful to make sure that we're only dealing with carbon 12 atoms, right? So if I have 12 grams of carbon 12, right? Well, first of all, that means that on average, this is going to apply to a sample of carbon, but we define this through only carbon 12, right? Avogadro's number is the number of atoms in exactly 12 grams of carbon 12. So we're really able to recycle our numbers for U and apply them for grams. So what we can say is that 12 U per atom relates to 12 grams per mole of carbon 12, right? And in the example, the aside I just did, then we saw this scale-up factor going from grams to pounds, right? And that gives us a number. And this gives us a different number, but all we're doing is scaling up that number, right? This number, now let's talk about what this number is. This number turns out to be 6.022 times 10 to the 23. How do we use this? We use this on a per mole basis. In other words, this is things per mole or atoms per mole or anything per mole. So the base unit for this is per mole, okay? Now this presents us a whole series of problems that we can use to practice and do some more dimensional analysis to try to understand this number. But this is a really big number, right? You can go on the internet and find all kinds of representations. If 1 million people counted 1 second, how many billions of years would it take 1 million people to count Avogadro's number of seconds? That kind of thing. It's a ridiculously large number, right? So here's the different various ways that we can use to represent this as a conversion factor. Okay. Now the nice thing about this is that now we have a macroscopic one-to-one basis of comparison between all of our atoms on a per mole basis, right? So if we have 26.98 grams of aluminum, we know we have 1 mole or Avogadro's number of atoms. If we have 10.81 grams of boron, we know that we have 1 mole or Avogadro's number of boron atoms, and so on, right? So it gives us a consistent basis of comparison for all of our macroscopic numbers that we want to deal with. Okay, so let's do a check here. How many copper atoms are in 63.55 grams of copper? Well, if we look on the periodic table, we find copper, right? Cu, whoops, Cu, and down here it says 63.55 for copper. This means 63.55 grams of copper equals 1 mole of copper equals 6.022 times 10 to the 23 atoms of copper, right? So the way we set this up, we almost really don't even need to do it. If we see that the mass in the periodic table is the same as the mass that we're given or we're concerned with, then that is 1 mole. It becomes a little bit more interesting. Let's do another example. Let's just take a round number. 100 grams of gold is how many atoms of gold? Okay, well, it turns out that if you look in the periodic table, for gold, we find that the mass, the molar mass of gold is 197.0 grams per mole. Remember, this is also 197.0 U's per atom, right? So let's start by setting this up. Let's set up the 100 grams. I gave myself an extra sig fig there. Shouldn't have done that. Right? We want to multiply this by the molar mass. 1 mole of gold is 197.0 grams of gold. And then we're going to multiply by Avogadro's number, 6.022 times 10 to the 23. Per mole. This turns out to be 3.06 times 10 to the 23 gold atoms. Still a huge number, right? It's a little more than half a mole, right? In other words, 100 over 197 is about 1/2, right? So we should expect our answer to be about half a mole, or about 3 times 10 to the 23 atoms. I always think you should have a pretty good idea about the number, right? In other words, this number should be very large. 10 to the 23 makes sense. If you get an answer that's 10 to the minus 22 or 10 to the minus 24, you probably inverted your number somewhere, and you should recognize that fact and try again. So let's look at this number that actually the book gives you the mass of a U per gram pretty early in the text, but I really don't like that, right? Because just like Avogadro's number is unimaginably big, the mass of 1 U in grams is unimaginably small, and it doesn't really serve you well to try to memorize this number, but it is easy to calculate, right? Let's see how this is. We know that there's 12 U's in 1 atom of carbon-12, right? I should have set that up here. For 1 carbon-12 atom, there's 12 U's for a mass, right? Now, if we multiply this number by Avogadro's number, that tells us how many U's are in a mole, right? And we also know that this equals 12 grams per mole. It turns out to do this conversion that you just divide by Avogadro's number. In other words, 1 over Avogadro's number in grams is the number of grams in 1 U. And that turns out to be 1.66 times 10 to the minus 24 grams per U. Okay? If you can memorize this number, remember it, that's fine. But if you can't remember this number, all you have to do is invert Avogadro's number, and you have the number of grams in 1 U. Okay? So let's check this, right? Because this question actually should be very simple once you understand the size. Which of the following is the closest to the average mass of 1 atom of copper? Now, all these answers are in are in grams. So 1 atom of copper, I don't remember exactly what that number is, but it's a really, really small number, right? So let's look at our numbers, 63 grams, 52 grams. These are all really big numbers. There's only one number that's really, really small in grams. So the answer has to be that last one, right? This is a very kind of obvious example, right? You have one choice that's very different than the others, and that happens to be the right size. So it has to be that answer. If you get a kind of a more normal question that has a bunch of big numbers and small numbers, you have to be a little bit more discriminating. But here's the calculation, just so we can make sure that we've done this properly. All right, here's another very common conversion. How many iron atoms are there in 4.48 moles of iron, right? This answer should be big, right? In other words, we have 4.5, 5 moles of iron, so this should be 4.5 or 5 times Avogadro's number, which is big, so the answer should be big. This is the way we set it up. We're going to end up canceling the moles of iron, and the answer turns out to be 2.7 times 10 to the 24 iron atoms, right? So this number should make sense to you. Here's another example. A sample of 26.98 grams of aluminum has the same number of atoms as blank grams of gold. Well, we just used gold, so we should be familiar with the molar mass, but we should also recognize this number, 26.98 grams of aluminum, as being 1 mole of aluminum, right? So all we have to do is find the molar mass in the periodic table, and it happens to be 197, right? So 1 mole of each, we just read the mass in the periodic table. Now, here's a little bit different question, right? Which of the following 100-gram samples contains the greatest number of atoms? How do we do this problem, right? Let's before we start this problem, let's write down what we have: magnesium, zinc, and silver. And let's write down their molar mass in grams per mole. Magnesium has a molar mass of about 24. Zinc has a molar mass of about 60, 65. I'm not going to go into too much detail because we don't have to get the answer here. And silver is about 107 grams per mole. Okay, so let's see how this works. Let's do a sample calculation. 100 grams of magnesium, right? How do we figure out the number of moles? 1 mole of magnesium is 24 grams of magnesium. This turns out to be about 4. But if we look at our sample calculation, right, we can see that we're effectively dividing by the molar mass. So what we should be able to see is as molar mass goes up, number of moles goes down, right? So in other words, we should see from these numbers that 100 grams of silver is pretty close to a mole. 100 grams of zinc is a little bit less than 2 moles, but 100 grams of magnesium is a little bit more than 4 moles of magnesium. So if we do the numbers, we can see that magnesium is the answer. But in general, it's probably more important to realize that as molar mass goes up, the number of moles goes down. In other words, we need more stuff, more mass of stuff to attain the same number of moles of stuff. Okay. Now, this applies to number also, right? In other words, whether we figure out the amount, the number in moles or atoms, they're really the same thing. They're really number amounts, right? And what we find out fairly quickly is it's actually rare to need the absolute number of atoms, say in Avogadro's numbers, or molecules in Avogadro's numbers. That's why we use moles so much, is because it's a legitimate stand-in for number. So we can apply the same thing here, right? The number of moles is proportional to number of atoms, right? So we want to put these, the easiest way to do this is, again, to put it in moles. 107.9 grams is the molar mass of silver. So this is 1 mole of silver. The molar mass of zinc, right, if we go back up a little bit, we can see this is about 65. So for zinc, this is greater than 1 mole, right, a little bit more than 1 mole of zinc. And for magnesium, right, the molar mass of magnesium is 24. So this is a little bit less than 1 mole, right? So since mole is a number amount, just like actual number of atoms, then all we have to do is pick the one that's the largest number of moles. We go with the one that's a little bit more than 1. And the order here, I guess it's asking the order, not the absolute one. This is first, this is second, this is third. In other words, B, A, C. So a big part of this chapter is getting used to these types of calculations, working with really big numbers, really small numbers, converting between moles and atoms and mass, right? And this is something we have to become comfortable with because it's usually the very first thing we do in every other calculation for the rest of the semester and really the rest of our lives as chemists. So we want to spend a few minutes to think about how are we going to solve problems here. We want to think about what is our answer? Where are we going, right? So we want to try to figure out maybe the units of the final answer. Are we looking for atoms or moles? Or maybe like this previous thing we just did, maybe we can use moles as a stand-in for number, right? That simplifies our work a little bit. How do we get there? Well, maybe we want to work backwards from the final goal to decide where to start. This last thing we don't want to forget either. Does the answer make sense, right? Is my number going to be really big or really small? Let me give you an example. How many atoms are in 5 moles of gold? Well, this number should be larger than Avogadro's number, right? In other words, it should be 10 to the 23 or 24 or even 25 atoms, right? So if our answer doesn't fit within that limitation, then we know we've done something wrong. On the other hand, if I'm asking you the mass of 1 billion gold atoms, right, this number should be very small in grams, right? So it might be 10 to the minus 20 or 10 to the minus 18 or 10 to the minus 19. The particular details of that, we would have to do the calculation, but we should expect a number 10 to the minus something as opposed to a number of 10 to the plus something, right? So let's talk now about molecular mass, right? So what we've been talking about technically so far is atoms, but let's think now about molar mass or molecular mass. This is the mass in grams of mole or moles of compounds. And we're going to take advantage of the fact that mass is considered to be additive. And it really is unless we're doing nuclear reactions. So this is really nice. So if I want to know the molar mass of ammonia, well, first of all, I need to know the formula, right? So nomenclature is very important. We need to know how to name these things. This is going to be the mass of 1 nitrogen, right, plus 3 hydrogens, right? And of course, this is going to be in moles, right? So I'm going to have 14.01 grams plus 3 times 1.008 grams for the hydrogen. This is going to be about 17.03 grams per mole of ammonia, right? And here's some other examples. Water, the molar mass is 18 grams per mole. And for barium nitrate, right, when we get something complicated like barium nitrate, a salt, right, we want to maybe build this up, right? So what we have is we have 137.33 grams for the barium. Plus, well, we have 2 nitrates, right? So let's figure out the mass of 1 nitrate, 14.01 grams plus 3 times 16.00 grams. And this turns out to be 261.35 grams per mole for barium nitrate, right? Now, one question that students often ask is, how many decimal places should I keep when I calculate molar mass or atomic masses, right? They're really the same number. And generally, I'd say most chemists go with 2 decimal places. As you'll see in these problems, the one common exception is hydrogen. I think most people with hydrogen like to go to 1.008. Just because its mass is so small, we want to give ourselves a similar number of significant figures. And for hydrogen, since its mass is around 1, lots of people like to go to 1.008 to attain that same number of significant figures. All right, so let's review some common calculations we have to do for molar mass. First of all, let's just calculate a simple molar mass of a compound. What's the molar mass of nickel 2 carbonate? Well, of course, at this point, we need to have a very good handle on nomenclature in order to know what the formula is. Right? Nickel 2 carbonate. Nickel 2, of course, has a charge of 2. Carbonate has a charge of -2, so here is the formula of the compound. Once we know the formula of the compound, we just have to write down the constituent parts, right? Nickel is 58.63 grams per mole. Carbon is 12.01 grams. And each oxygen is 16, so there's 3 of them, or 48. So we add this all up, we get 118 grams or so, and so the actual mass is 118.7. Okay. Let's look at another example, ranking. Very often we want to get a general idea of the composition of things without doing a detailed calculation, so we should discuss how to do this. Consider equal mole samples of N2O, Al, NO3, 3, and KCN. Rank these atoms, or rank these from least to most number of nitrogen atoms in each sample. Well, here, atoms can be stood in for by Avogadro's number. In other words, I can use a mole of things or moles of atoms to stand in for the absolute number since they're both number amounts. So really all I have to do in this question is figure out how many atoms of nitrogen are in each of the compounds, right? And this should be relatively easy at this point. N2O has 2 nitrogens, AlNO3 3 has 3 nitrogens, and KCN has 1 nitrogen, right? So the rank from least to most is going to be KCN to N2O to Al, aluminum nitrate, AlNO3 3. So this is a more general question. And one of the things that you can do is you can practice figuring out a question like this without actually doing the math on your calculator. Here's an example of that kind of thing happening, right? Now, this is a little bit more complicated because I'm going to have the same mass of each of these compounds, and I have to convert this to a number amount, right? So molar mass is going to be important here. I'm going to have 100 gram samples of H2O. Molar mass is about 18. N2O, the molar mass is about 44. C3H6O2. This also has a molar mass of 44. And CO2, which also has a molar mass of 44, right? So if we have 100 gram samples here, let me do a sample calculation for 2 of these so we can kind of see the pattern. For water, if I have 100 grams of water, right, the first thing I want to do is convert to moles of water. 1 mole of water is 18 grams of water, right? So at this point, I'm going to have moles of water. 100 grams of water divided by the molar mass gives me the number of moles of water, right? But I want to know oxygen atoms. So let's convert this to number of oxygen atoms, moles of oxygen atoms. There's 1 mole of oxygen atom and 1 mole of H2O, right, which we could see from the formula, right? Let's do the same thing for N2O. 100 grams of N2O, 1 mole of N2O. Now, the mass here is different, 44.0 grams per mole. But there's still 1 mole of oxygen and 1 mole of N2O, right? Now let's look at these, and without doing the other 3 examples, let's get a general answer here, right? In other words, this first one for water is 100 divided by 18. This is a little more than 5, right? A little more than 5. Let's look at the N2O, 100 grams divided by 44. This is a little less than, or a little more than 2. So if I was just considering these two, right, just these two, then water has more oxygen atoms than N2O in 100 grams, right? The first thing we have to do is convert this to moles. If you continue on for the other two, there's only a total of 4. The thing that's going to be important here is the molar mass, right? Because the molar mass and the number of oxygens, right? So it turns out that water wins. Water has the most number of oxygen atoms on a mass per mass basis than the other compounds. This should not be too surprising because its molar mass is the smallest, right? You might want to think about that a little bit. Okay. Finally, let's figure out the number of grams of fluorine in 1 molecule of boron trifluoride. Boron trifluoride is BF3. Now, in order to do this problem, we've just written down here at the bottom, we start with 1 molecule of BF3. We multiply by how many atoms of fluorine there are in 1 molecule of BF3, 3 to 1. At that point, we have the total number of atoms, right? But since we want the mass in grams, right, then we're going to have to introduce Avogadro's number. If we wanted the mass in U, we would not have to do this. So we divide by Avogadro's number, moles to atoms, right? And that's because of this here. 1 mole of fluorine is 19 grams of fluorine, right? So this introduction of grams per mole forces us to divide by Avogadro's number. So the answer is going to be really, really small, right? So we know we can get rid of these two because those answers are really, really big. Now, if you're at this point and you're a gambling kind of person, you can just guess on one of these two answers that are more plausible. If you're running out of time on a test or something like that, now you've given yourself a better chance, at least, right, to guess the right answer. If you have time and you do the math, it turns out that it's B. All right. Let's now talk about mass present as a composition. Mass percent is a fairly common composition that chemists use to communicate with other people, right? In other words, let's say that you want to fertilize your new fruit trees and you're looking for a fertilizer that's high in nitrogen content, right? As a normal kind of everyday person planting trees in their backyard, you're not really so concerned about the formula is or having to figure out the molar mass or anything like that. For you, all you want to know is what's the amount of available nitrogen in mass percent for your bag of fertilizer, right? If you're looking for the most amount of nitrogen possible, then a 40 mass percent bag of fertilizer, 40 mass percent nitrogen in a bag of fertilizer is going to be better for you than a 15 mass percent nitrogen, right? So we have to be able to convert and talk about mass percents. Well, mass percent is just going to be the mass of our element divided by the mass of the compound times 100. And over here it says in 1 mole, but I would say that you can think about this on a mole or individual atom basis, right? Because the law of constant composition says that if we know the formula of the compound, it doesn't matter how much of it we have, the composition is the same. So you can use whatever unit you want to, but we typically use molar mass, right? It turns out the actual U or G does not matter. Again, you might want to think about that a little bit, right? So here's an example for the amount of carbon in ethanol, C2H5OH. The mass of carbon in this compound is 2 moles of carbon for every 1 mole of compound, right? So we have 12.01 grams, the molar mass of carbon, 24 grams. So this is going to be the thing that we're interested in for the carbon, but we also have to figure out the total molar mass of the compound. So we have to add in the hydrogen and the oxygen, and we get 46.07, right? But for carbon, C2H5OH, I guess the final answer is not really on the slide. I wonder why that is. The percent carbon by mass in C2H5OH would be 24.02 grams of carbon. Don't need to put that twice. Divided by 46.07 grams of the compound times 100. Just a little more than 50%, right? 24, 46.07, 52.1% carbon. 52.1% carbon by mass. Now, you'll notice that most chemists, most professors, graduate students, or other people, when we're talking about mass percent, we go through and say 52.1 carbon by mass. And it might seem a little bit silly or anal retentive, right, to say percent carbon by mass. Of course it's by mass. That's what we've been talking about. But there's many different kinds of percents that you can calculate in science. So we want to be absolutely clear when we're talking to other scientists or students to make clear this is a mass percent because there's volume percents and other kinds of number percents that we can come up with too. So we want to be absolutely 100% clear about this. Here's another example. Morphine, derived from opium plants, has the potential for use and abuse. Here's the molecular formula, C17H19NO3. So the first thing we have to do in this calculation is we have to figure out the mass of the entire compound, right? This is not broken out separately in this example, but it's 17 times carbon plus 19 times hydrogen plus nitrogen plus 3 times oxygen. If we want to know the percent mass by carbon, then the total carbons are 17, so we multiply 17 by 12.01, and this turns out to be 71.6% carbon. All right. Here's another example of the oxygen content in these compounds that we saw a few minutes ago. Well, here, let's write this out. The percent oxygen by mass is going to be the amount of oxygen in grams divided by the molar mass of the compound times 100. All right. Now, if all we're asking for is a ranking, not the absolute number, then maybe we can just write down the expression and see what the size of the answer is going to be and do the ranking, right? For H2O, there's one oxygen in each molecule. This is going to be 18, not 18. It's going to be 16, the mass of one oxygen, divided by 18, the molar mass, times 100. That's pretty close to 100, right? For N2O, remember the molar mass of N2O was 44. This is going to be 16 over 44 times 100. For C3H6O2, this is going to be 2 times oxygen's mass, or 32. The total mass is 44, I believe I said before. And for CO2, this is also, that doesn't look right to me now, 32 divided by 44 times 100. Let me take a second and check this answer for C3H6O2. Yeah, I knew that was wrong. It's 74, not 44. That makes the answer a little bit more apparent. So at this point, we can see, right, just by writing these out without writing the number, that this is water's the winner. It's the most oxygen by mass. And it looks like CO2 is number 2, and N2O is going to be the smallest, right? Okay. All right. Now let's talk about empirical formulas. Empirical formulas come about usually because if we analyze a compound by mass, percent by mass, one of the questions that comes up is, well, we can take a formula and we can get the percent by mass from the formula, right? We've shown that with a few examples now. Can you do the opposite? Can you take the percent by mass and get a formula out of it? And the answer is mostly. And to understand the mostly part, we need to talk about empirical formulas. Empirical formula of a compound is the ratio in the formula expressed in the smallest integer ratio, right? Now, most of the time, or many times I should say, the empirical formula is the same as the molecular formula. So let me write this down. Smallest integer ratio formula, right? So let me give you an example. H2O, this is 2 to 1 hydrogen to oxygen, right? We can't reduce any of those numbers anymore. So for water, empirical formula equals the molecular. But H2O2, hydrogen peroxide, right? This is 2 to 2, which is the same as 1 to 1. So the empirical formula would be HO, right? H1O1. Notice it's different from the molecular formula, and these two are not the same. Let me give you another example, right? Copper sulfate, copper 2 sulfate, right? We have 1 to 1 to 4, copper to sulfur to oxygen, right? So here the empirical equals the molecular. But what if we have mercury 1 iodide? Mercury 1 iodide. Remember, mercury 1 is funny, right? It's a dimer. It looks like each mercury is a +1, but it actually doesn't exist that way. It exists as 2 together with a +2. The empirical formula for mercury 1 iodide is HDI, right? So here the molecular is not equal to the empirical formula, right? But let's look at the mass percent mercury in Hg2I2, right? This is going to be 2 times the mass of mercury over the mass of Hg2I2, right? And notice that this is the same as 2 times the mass of mercury times 2 times the mass of Hg plus I, right? And what happens here is these two cancel. So it turns out that the mass percent for a compound for an empirical formula is the same as a molecular formula. So this is the problem we have if we take mass percents and get a formula from the mass percent, is all we can say without additional information is that this gives us the empirical formula of the compound. Okay. So here's another simple example. Empirical formula for a hydrocarbon might be CH, right? Turns out there's no stable compound of carbon and hydrogen that has the formula CH. There is C6H6. One type of C6H6 is called benzene, very common compound. But since the numbers of each of the carbon and hydrogen is just 6 times the simple ratio of 1 to 1, then the mass percent's the same whether or not it was C6H6 or it's just simply CH. So without additional information, it can be impossible to tell whether we have an actual molecular formula or an empirical formula once we're done. Well, there are a number of steps to take to figure out the formula from mass percent. And again, I'm going to write down the law of constant composition. Very important law in science and chemistry. The law of constant composition says the composition of your compound is the same no matter how much of it that you take, whether you take a kilogram or a 55-gallon drum or a pound or an ounce or a gram or 100 grams. So since we can take any amount that we want, the easiest thing we're going to do is we're always going to assume that we have 100 grams of our stuff, right? If we do this, then the mass percent translates easily to grams of that element, right? So let's run through this simply with this problem example here. A gaseous compound containing only carbon and hydrogen was analyzed and found to consist of 83.65 carbon by mass. Determine the empirical formula. Okay, the first thing we're going to do is we're going to assume that we have 100 grams of this hydrocarbon. And if we do that, then this 83.65% by mass of carbon gives us 83.65 grams of carbon, right? So that we see that here. The other thing we have to realize is that the sum of the percents by mass has to add up to be 100. In this case, we only have two things, carbon and hydrogen. So the percent by mass hydrogen is going to be 100 minus the 83.65, 16.35, right? So now we have the mass amounts, the mass ratio of each element in the compound that corresponds to the chemical formula. So the second step is convert the grams of element to moles of element, right? In this case, we take 83.65 grams of carbon, divide by the molar mass, or multiply by 1 over the molar mass, whichever way you'd like to think about it. This gives us 6.965 moles of carbon. So let's write down, we'll call it a pseudo formula, right? The amount of carbon we have is 6.965 moles, right? The hydrogen calculation is 16.35 divided by 1.008 grams. This gives us, into our pseudo formula, of 16.22 moles of hydrogen. This ratio of carbon to hydrogen is a number ratio. But it doesn't work for our chemical formula, right? Because our chemical formula uses integers. How can we turn these into integers? We divide out by the smaller of the two numbers, right? We divide out by the smaller of the two numbers. So 6.965 divided by 6.965 is obviously 1, right? So that gives us carbon 1, right? And the other number, 16.22 divided by 6.965 equals 2.33. So that gives us carbon 1, H 2.33. We're still not there though, right? Because we still don't have two integers. We have one integer and one decimal. But what we want to do is we want to realize 0.33 equals 1/3 in decimal terms, right? So what this means is we have C1, H2, and 1/3. And the easiest way to see the next step is if you have this. Well, let's slow down. Let's back up. Let's think about some other decimal representations of fractions that we might want to look for. 1/2 equals 0.5. Now, remember that when we do calculations, they don't always come out perfectly. So it might be a little bit different, right? So if you get 0.48, 0.51, that's probably going to equal 1/2, right? So we want to look for numbers close to this. It's not always going to be exactly this. 1/3, of course, is 0.33. We see this up here. 1/4 equals 0.25. 1/5 equals 0.2. This is usually the limit of the decimal representations of fractions that we see in problems. So these are the ones you want to worry about. All right, so what do we have here? We have C1, H2 point 2 1/3, right, is what we said. 2 1/3. Okay, well, let's put this into mixed fractions to see this better, right? In other words, common and mixed fractions. What is 1 in terms of thirds? 3 over 3. What is 2 and a third just purely as a mixed fraction? It is 7 thirds. So now we can see we have common denominators, right? And we can see that the 3 over 3 to 7 over 3 equals 3 to 7. C3H7. So this is our empirical formula, C3H7. This may or may not be the actual molecular formula, right? I keep saying that we have to have additional information. What is this additional information needed to solve this problem? It might be something like, how many moles do we have? We might be using some gas law problems. We haven't done gas laws yet, but remember this type of problem, because when we talk about the gas laws, I'm sure we will apply gas laws to this problem. Okay, so here's one you can try on your own. You should try this one on your own to see what you come up with. Adipic acid. This is a common name, right? It's not a systematic name. It's a very common acid found in nature and in food, adipic acid. C3H5O2. This looks a lot like C2H3O2, right, which is acetic acid. Adipic acid and acetic acid are structurally kind of similar. All right. Well, once we have an empirical formula, how can we calculate a molecular formula? Remember going back to this example a few minutes ago of CH and C6H6 having the same empirical formula? There's just some sort of scale-up factor or conversion between the two. This is going to be an integer. This is going to be, we're just going to call this the n number, right? So the molecular formula is going to be our empirical formula multiplied by some factor. In other words, we're going to multiply the coefficients on each element by the same factor, right? So here's an example of additional information that allows us to solve our problem, applied to our C3H7. The gaseous compound containing carbon and hydrogen was analyzed and found to consist of 83.65% carbon, yada, yada, yada. The molar mass of the compound is 86.2 grams per mole, right? So what we're going to do is we're going to calculate a empirical formula mass of our C3H7, right? This is going to be 3 times 12.01 plus 7 times 1.008. This is going to be about 43 grams, right? This is the mass of moles of this empirical formula, right? We can think about this as a fragment of a larger molecule or whatever. And usually when we do this, we don't have to get too specific with the number. In other words, usually getting it without any decimal places at all is good enough to tell us what the n is. The idea here is the molar mass divided by this empirical formula mass is going to give us our n, right? And in this case, it's 86.2 divided by this 43, which is 2, right? Usually, again, we don't have to calculate this exactly. We can usually see what the factor is, right? Then we're going to take C3H7 times 2 equals C6H14. And this turns out to be hexane. Hexane has this formula, N-hexane has this formula. Okay, so that's generally how we do these calculations of molar mass. If we get this additional information for adipic acid, we find out that now the formula is not C3H5O2, C6H10O4 turns out to be its molecular formula. Okay, now that brings us to the end of the slides, but I do have one more problem I'd like to do to practice this empirical formula, right? And this is a problem in your book. This problem says 3.269 grams of zinc is heated in pure oxygen. The sample gains 0.8 grams of oxygen. Calculate the empirical formula. This is a good problem to do because if we think about it a little bit at the end, we know what the answer is. In other words, maybe you know it right now. If I have a compound of oxygen and zinc, what's the formula? You'd probably figure that out right away. So we kind of know the answer, but many times in this type of problem, we're not necessarily going to know the answer, so it's good to do a test case where we can test it against our previous knowledge, right? So 3.269 grams is zinc only, right? And it gains 0.800 gain of oxygen is oxygen only. So the way we're going to do this is we're going to convert both to moles, convert both masses to moles, and then put this into a mole ratio or a formula. Very similar to what we did a minute ago with our other examples, right? Let's start with the oxygen. 0.800 grams of oxygen, right? 1 mole of oxygen is 16 grams of oxygen. This is 5 times 10 to the minus 2 moles of oxygen, right? Okay, 3.269 grams of zinc. 1 mole of zinc is 65.38 grams of zinc. This gives us 5 times 10 to the minus 2 moles of zinc. In other words, if we kind of follow the same pattern we did with the other problem, we have zinc 5 times 10 to the minus 2, oxygen 5 times 10 to the minus 2. Those numbers are the same, so we can see trivially the formula is ZnO. Does this make sense? Well, zinc's common charge is +2, oxide's common charge is -2, and we already kind of know. Remember how we figured out formulas from names as we crisscross the charges to the subscripts? Zn2O2. But when we do this for naming, we know that we just reduce that number to ZnO, right? When we talk a little bit more about the structures of ionic compounds, we'll come back to this idea because it turns out that for ionic compounds, all we can really get is the empirical formula from this. So for an ionic compound, the molecular formula really is an empirical formula to begin with, which is kind of interesting. So we'll think about that again when we talk about atomic molecular structure a little bit more. Okay, so that brings us to the end of Chapter 8's lecture. Hope it was helpful for you. Remember, at any time you can send a Canvas or a regular campus email to myself or Dr. Zhao or Dr. Stare if you need some help. I hope your semester's going really well, and we'll talk again soon.